so what you see is that x1 plus x2 plus x3 must equal to 0, right? That is to say that any solution is going to look like minus x2 minus x3, x2, x3, right? Where x2 and x3 can be any number. So the solution set looks like this, right? And you rewrite that more cleanly as x2 times negative 1, 1, 0 plus x3 times negative 1, 0, 1. So you see that two-dimensional, that the eigenspace is two-dimensional. The geometric multiplicity is also 2, which is good. So this guy would be diagonalized. Here.
Well, actually, how would the basis of that look like in terms of the eigenspace?
So you're wondering what happens when we diagonalize? Well, so we would calculate, you would also need to calculate E2, right? E2, if you do it, turns out to be the span of 1, 1, 1. Okay. And so then you have something similar. Right? You have that if you conjugated the original matrix, right? If you conjugate the original matrix 0, 1, 1, 1, 0, 1, 1, 1, 0, and you conjugate that by these guys, say 1, 1, 1, negative 1, 1, 0, negative 1, 0, 1, and its inverse. 1, 0, 1, 1, 0, 1, okay. You're going to end up with what?
2, 1, or is it 2, 1, 1 all the way?
It'll be 2 negative. This guy gets multiplied, this guy gets scaled by 2, these other guys get scaled by -1. So lucky for us, the geometric multiplicity for -1 also turned out to be equal to the algebraic multiplicity, and so we can get a basis of eigenvectors and diagonals. And like I said, this doesn't always happen. The eigenspace could have turned out to be one-dimensional, right? And then you're in trouble. You need to use the generalized eigenvector, which we'll do later. Okay. Is everyone all right? Don't be nervous, George. It's easy. For those of you who haven't had linear algebra, how did you get into this class anyway? I don't know. But it's okay. It's easy. It's actually easy. So if you feel nervous, just come to office hours and I'll explain. I'll say exactly the same thing. Yeah, I'll explain it in a different way. Okay. So that is the end of the linear algebra review. So a couple minutes, and let me sort of just give some hint or indication of why we want this linear algebra review. So let's go back. Let's return to the system A y double prime, second order system of constant coefficients. We learned how to do this a long time ago, right? We took e to the lambda t, we substituted it in, we got something that we call the characteristic polynomial, right? We solved the characteristic polynomial, and then we said, okay, any solution is going to be c1 e to the lambda 1 t plus c2 e to the lambda 2 t, as long as those things have different roots. Right? Okay, and at that time, people asked, is this characteristic polynomial the same thing as the characteristic polynomial that I learned in linear algebra? And the answer is yes. Okay, so here's the connection. Okay, let me just divide by a to make things convenient. So I'm going to take this second order system and I'm going to change it into two first order equations. So let x1 be y and let x2 be y prime. Okay. So in that case, what's the relation between my x1 and x2? Well, x1 prime is x2, right? x1 prime is x2. x2 prime is y double prime. Well, y double prime, right? Y double prime is negative b over ay prime minus c over ay, right? Well, that's negative b over ay prime minus c over ay, right? Because y prime is x2 and y is x1, right? So what I've done is I've taken this second order equation and I've basically taken all the information in it and I've expressed it in terms of two first order equations, right? Okay. Of course, we can rewrite this using matrices, right? This is the same thing as saying that you want some function, right? x1, you want some vector value function, right? You want some, well, let me write it in terms of matrix first, and then I'll say. You want something that satisfies this, 0, 1, negative c over a, negative b over a, x1, x2. Right? The same thing, right? The same thing. And so what we're looking for, we want a vector value function. Right? X vector t, right? Such that x vector prime t is equal to a x of t. Right? And if we can find that vector value function, then we've solved our equation. And so notice that if we take the characteristic polynomial, if we take the determinant of this thing minus lambda I, we get minus lambda 1 over c over a b over a minus lambda. You end up with lambda squared plus b over a lambda plus c over a is equal to 0. It's that, and you see that right, that equals 0. Right? This equals 0 is the same thing as saying that a lambda squared plus b lambda plus c is equal to 0. Right? And so the characteristic polynomial that we got out of the second order equation so long ago is actually the characteristic polynomial of the corresponding matrix. Right? When we transform this thing to a matrix equation. And so next time we'll start tying things backwards and going forwards.
And show
and how to solve.